Alright everybody, I hope you're still enjoying the review. We're going to go over another method of approximation. In one of the other videos I covered was the midpoint rule, where we just took the midpoints of our little interval. Here, I'm going to take the trapezoid rule, which sounds almost exactly like it, right? We want to approximate our function into a series of sums of trapezoids. So if we take this function, we have the bunch of points here. Then our hypothesis is that we can better approximate it if we have a better defined curve, right? And that better defined curve, in our case, we're going to say is a trapezoid. Which will be here, here, here. So if you see, I'm kind of doing the drawing bad justice, right? I mean, there would be a lot more error here and here if we had the trapezoid. But the basic idea behind the trapezoid rule, right, is we take our function and let's exaggerate it. So, right, this is a regular horizontal trapezoid. And the way that we would calculate the height of the area of a trapezoid is by taking this height and then taking this base and this base, right? A plus B, right, times the height, all over 2. That's going to be the area of a trapezoid, right? That'll give us all of this area. Now, if we, I guess, rotate it 90 degrees, we can sort of see the immediate application of what we're doing, right? Here, here, right? So here our height is the same, right? This is our height. This is our A. This is our B, right? And so we're still going to have the same height, except this doesn't look like the height. But in this case, if we apply it to a function, we have 2 points here and here, right? Let's say here, here. Then our function, right? We can sort of say, okay, well, it's approximately going to look like this trapezoid here. And this trapezoid here, right? If we map it onto our little XY map, right? If we choose our point x naught here, x1 here, right? Then our height is given by x minus x naught, right? And this is going to be the basic delta x definition, right? The change in x variable. And then our height, right? Our little bases here are going to be given by the heights of, right, a and b. The heights of a and b are given by the functions, right? So it's f of x1 and f of x2, or x naught, x1. All right, so there we have the two values for a and b, and now we have a width here. And now we want to continue this, right? We want to continue this trend. And so we want to keep on adding these up. So whenever we do that, we take f of x naught plus f of x1, right, times delta x, right, all over 2 plus, right, and we want to continue from f of x1, right? This is going to be, this f of x1 is going to serve as one of the bases for our next integral whenever we iterate through this function. So our next trapezoid is going to be given by f of x1 plus f of x2, right, times delta x, because we're choosing delta x to be the same no matter what, right? And we continue this until we do f of x n minus 1 plus f of x n, right, all over 2 times delta x. Right, and if you notice here, some of these 2's are going to cancel out, because if we distribute all of these terms, right, we're going to get something that looks like this. Right? If we continue doing that calculation, we're going to get these terms are going to be repeated. So we're going to have 2 of these. All right, but there's a delta x divided by 2, so we pull all of these out. All right. And we're going to have 2 of these x1s, x2s, x3s, right? So we're going to have f of x naught plus 2 f of x1 plus 2 f of x2. Right, we continue, and 2 f of x n minus 1 plus f of x n. Right, so notice we don't have 2 here because these are only serving as a height for one of the bases, right? One base. But this one trapezoid base, right? But this f(x1) is serving as a base for this integral and or this trapezoid and this trapezoid. So for each of the intermediate x's, right, it's serving as a base for 2 trapezoids until you get to the ends. They're only serving as one base for one trapezoid. So doing that, let's take the same function we had last time. We want to integrate 1 over ln of x from 2 to 3. And then we want to say, okay, well, now we're going to use the trapezoid rule. We've gotten the general formula, delta x over 2 times, right, f of x naught plus 2 f of x1, continue, right. For this calculation, it's a little bit more involved because we have the 2's, and sometimes we don't have a factor of 2. And sometimes we do. But here is basically the calculation that you'll get whenever you do it for this integral. So you get 0.1 over 2, right? We've chosen that n equals 10, like we did for the midpoint rule. And so then we take the f of f2 plus 2 times f of, which one is it? F of 2.1 plus 2 f of 2.2, all right, plus 2 times f of 2.9 plus f of 0.9. So whenever you do this, you're going to get, so for this one, we're going to get a 0.1 divided by 2 times f of 2, which is going to be 0.1 over 2 times 1.44269 plus, and then these 2's are going to cancel, so we're just going to have the 0.1 times 1.3 right, so this 2, whenever we distribute, is going to cancel with this one, this one, this one. So if we continue this calculation out, right, to f of, sorry, this one should be f of 3. 0.1 divided by 2 f of 3. Whenever we perform this integral, there might be some error based on what numbers you round to, or what your calculator position is. 1.118 something. Here I only rounded to 3 digits, but from our previous example, this is approximately what we're going to get. And this is actually going to be the important difference to tell us the error whenever we do all these calculations. But that's the basic idea behind the approximations. You just want to take 2 times the f of the interval, and then, or f of, right, our different discrete points. And you should get the right answer. All right.